So, hello everyone, welcome to class 13. So, again we will continue towards looking at the trigonal systems today, which have 3-fold and 6-fold or 3 bar and 6 bar axis of symmetry. We have already seen so how the monoclinic, the triclinic, monoclinic, orthorhombic, then the tetragonal and the cubic systems come about. This is just by increasing the symmetry, the underlying symmetry. More triclinic has almost nothing, so 1 or 1 bar. Monoclinic is just 1 2-fold axis or 1 mirror, right? Then we have the orthorhombic system, which has more than 2-fold axis of symmetry or more than 1 mirror, right. Then we came to tetragonal system, where we said there should be 1 4-fold axis of symmetry, and so that gives the corresponding constraints on the unit cells that you can choose and define. Then we looked at cubic cells, cubic unit cells, which are defined by having 4 3-fold axis of symmetry, not 3 4-fold axis of symmetry. You can, with 4 3-fold axis of symmetry, you can actually show that A equal to B equal to C, alpha equal to beta equal to gamma equal to 90 degrees. That is quite a crucial point. And when we actually do point groups, I am going to show you materials which are cubic in nature, but they do not have 4-fold axis of symmetry. What they have instead is 4 3-fold axis of symmetry. Okay. Okay. So, today and then we said we will postpone the discussion on trigonal and hexagonal systems towards the end, and the end is here. So, so we will start by looking at what a trigonal and a hexagonal system is. Okay. So, why do not we start with what a hexagonal system is, and as the name indicates, so let me use a different color, let me go back to green. Hexagonal systems, as the name indicates, so you either have a 6-fold axis of symmetry or a 6 bar axis of symmetry. Now, 6-fold axis of symmetry is all right. I can do a stereographic projection, and I can say that if I have, and then I color this, if I have I have a hexagon like arrangement, right, of an asymmetric unit. Whereas 6 bar, we also did this. We said that if there is a 6 bar axis of symmetry, so I'm going to color just the middle part, then it's not, so it is equivalent to having so okay, so I'll come to this notation later. But if I have plus and minus, plus and minus, plus and minus, so this is equivalent to having a 3-fold axis of symmetry plus a perpendicular mirror, right, to the 3-fold axis of symmetry. So, that we are calling it as 6 bar. We are going to consider that as tetragonal system, but equivalently someone can just say that no, I would rather look at it as something which has a 3-fold axis of symmetry and a mirror symmetry, right. So, that is fine. So, as a result, defining a hexagonal system and isolating it from a trigonal system, which is defined by 3 and 3 bar axis of symmetry, becomes a bit tricky. Okay. So, there is some sort of vagueness there, but that is okay. So, in this course we are just going to say that 6 and 6 bar belong to hexagonal systems, and 3 and 3 bar which we separate out. If there is a 3 by m, this sort of 3-fold axis plus a perpendicular mirror, we are going to call it as a 6 bar symmetry operation. That is one operation, it is not 2 operations multiplied with each other. Okay. All right. So, 6 bar is one operation. So, with that caveat, so you can again go through so what will a 6-fold axis of symmetry do, and it becomes easy for you to define. I mean, the unit cell then becomes something like this. You have an A, B, and a C that is coming out of plane, but turns out that A equal to B, it does not need to be equal to C, right. So, and later the other constraint you have is that the angle between A and B, which is my angle gamma, is equal to 120 degrees, right. So, that is a hexagonal system in general. So, this is the base is a parallelogram with 120 degrees as the angle between A and B, A equal to B. So, instead of A, so I am just going to write this as mod A and mod A, and you have a C which is perpendicular. So, beta equal to alpha equal to 90 degrees, right. So, which is perpendicular to the basal plane. So, this is what is called a basal plane of the unit cell, right. The rest of them are what are called prismatic planes or pyramidal planes, right. So, for example, this plane is what is called a prismatic plane. Right. So, that is how we define a hexagonal unit cell, but in general, right. So, instead of so you can define a hexagonal unit cell with a base, so I have this is my A, this is my B. However, so I can look at the vector which is in this case this is A and this is B. So, this will be A plus B, right, or I can look at the other form of this vector which is A minus B, minus A plus B or A minus B, these sort of vectors, right. So, they are also perfectly good choice of basis for a unit cell, right. So, I can either take A B, I can either take A minus B, I can either take this vector and this vector or this vector and this vector, right. So, everything is at 120 degrees angle to with respect to each other, right. So, you will see that some people actually take all the three vectors, and so in a hexagonal system the Miller indices have 4 indices in them, not 3 indices, not saying that it is a 4 dimensional system, something like 0 0 0 1, something like 1 1 bar 2 0, or right. So, these sort of things, right. So, this does not say that or 1 0 1 bar 0, something like that, right. So, the 4 indices are not telling you that it is a 4 dimensional system, rather the 4 indices, these 3 indices will be related to each other, right. So, I do not think this is 1 bar 2 0, but yeah, okay, fine. Okay. So, these 3 indices are not completely independent of each other, right. So, in this course we are not going to use 4 indices, we are just going to use 3 indices in a hexagonal system, but so it should be h plus k equal to minus I, that is going to be h k I L, these are the indices, right. Okay. But we are not going to use this notation here. So, if you are using that notation, then you have a hexagon, right. So, you have an underlying hexagon which I am going to draw it like this, which should define sort of your unit cell, but so in our notation this hexagon has 3 unit cells embedded in it. This is 1 unit cell, this is the second unit cell, this is the third unit cell. Okay. So, and then this unit cell is going up the page, right. So, that is your C axis. Okay. So, although we will use hexagons to define 6-fold symmetry, our unit cell is still this unit, right. So, this unit here or this unit here, right. So, or the other unit. Okay. So, that is the caveat, right. So, you may see HKIL, but in this course we are not going to use HKIL, we are just going to use the A index, the B index, and we are just going to use an HKL sort of thing, with the additional constraint that A, B have an angle of 120 degrees between each other, and that is it. So, and C axis is perpendicular to the AB plane. Okay. So, that is your hexagonal unit cell. Now, let me actually, so this is I will draw it. So, that is the A axis, that is sorry, again let me just draw the C axis first. So, this is A and now this is B, and the angle between A and B is 120 degrees. Okay. Something like that on those lines. Okay. So that is your hexagonal unit cell, so the only difference between a tetragonal and a hexagonal unit cell is the angle between A and B, right. So that is 90 degrees there and it is 120 degrees here. Alright. So now let us actually look at what is a trigonal system, where I have 3-fold axis of symmetry or 3-bar axis of symmetry. Okay. So essentially this is better to explain with figures that are pre-drawn rather than me drawing a figure, right. So that is okay. So I can take a cube, right. So a cube has 3 I said 4 3-fold axis of symmetry, right. So this the 1 1 1, so the 1 1 1 is represented here. There are 4 body diagonals, each of these body diagonals is a 4-fold axis of symmetry, right. Now I take a cube and I compress the cube along one of the body diagonals, right. So if I compress the cube along one of the body diagonals, what I do is I am not actually removing that 3-fold axis of symmetry, whereas the other 3-fold axis of symmetry are being removed. Okay. So I stretch it or I compress it. This is equivalent to taking a square, right. So a square like this, and if I pull the square up so about its body diagonal, then this square becomes a rhombus, right. So I am losing some symmetry elements, right. But so similarly, if I take a cube and I pull it along one of the body diagonals, I am losing the 3-fold axis of symmetry which are about the other body diagonals, right, whereas I stretch it along this direction, right. So what I end up getting is what is called a rhombohedral, right. So from a cubic setting I can just pull one body diagonal and I kill 3 3-fold axis of symmetry and I retain one. Okay. So that is one way of coming to a 3-fold axis of symmetry. Take a cube, kill the other 3 and just retain one, and that can the operation can just be you take a cube and stretch it along one of its body diagonal. So that body diagonal is now special. The body diagonal along which you stretch the cube is somewhat special compared to the other 3 body diagonals, in that this retains its 3-fold axis of symmetry, whereas the other 3 they sort of stretch and compress in certain ways that you cannot retain the 3-fold axis of symmetry. Okay. So I mean, so this is the analogy in 2 dimensions is a square. So you have 90 degrees to start with, but once you start pulling it about the body diagonal, you lose your 90 degrees, you lose the cubic or the square nature of the unit cell, right. So it becomes a rhombus. Similarly here what I have is a rhombohedron. Okay. Now the other way of looking at a rhombohedron is from the hexagonal system, right. So here the 1 1 1 axis is your 3-fold axis of symmetry, right. So instead of looking at the 1 1 1 as a 3-fold, so instead of giving it complex indices, I am just going to call that 1 1 1 axis as the C axis, and if the 1 1 1 axis is the C axis, or so then I have an underlying hexagonal unit cell, right. So I can define a rhombohedron, right. So with, let us say this is the C axis, about the C axis I have this is the 3-fold axis of symmetry, and about that so I can also define a rhombohedral perfectly in terms of a hexagonal unit cell, right. So this is the hexagonal unit cell, right. However, it turns out that if I have a hexagonal unit cell like this, let me start here. So you can see that in plane, this is the basal plane of the hexagon, and since it is 3-fold axis of symmetry, I am just saying that about the C axis, if I have 3-fold axis of symmetry, I should have about 120 degree rotation, I should get exactly the same entities, right. So if I define, let us say there is point A to be my center of the basal plane, then so I can define my axis to be like this, right. So that is a perfectly good definition, because then I am representing the threefold axis by saying that this is 120 degrees, right. So the threefold axis of symmetry is somehow seen through the axis, which is the c axis. C axis in a cubic system happens to be 111, whereas in a hexagonal system happens to be 0001, or the c axis 001, or the c axis. Okay, that is fine. However, what I am going to do now is I have a hexagonal unit cell, right. So the same entity is again on the top. So the hexagonal, if I actually draw the cross section of it, it is going to be like this. So this is the plane in plane, and this is so this is the hexagonal unit cell, right. So and then these vectors are again here. So this is a hexagonal unit cell, right. So let us say the length of this unit cell about c axis is 1, right. So the length is 1. Okay. Now if you see these people here, so what they have done is, okay, so I start with this point, right. So this is my hexagonal unit cell, but there is a bigger hexagon, right. I don't know how to erase this. Okay, so let me rewrite this. So about this, so I have a bigger hexagon, which is my basal plane, and so at 1/3 the distance, right. So I am going to put these 3 points, right. So for example, so okay, so it's again equivalent representation in figure E here. So I have A, which is this, I have B, which is this. This is A hexagon, B hexagon, right. At a point 1/3, 2/3, 2/3, right. So so from A, so I put this circle, right. So this is along A, this is 1/3, along B of the hexagon, this is 2/3, right. And I am putting this along C, which I am not representing here, which is not shown in this plane, but this is a 2/3, which is somewhere here, right. So in this plane, this is the 2/3 plane, this is the 1/3 plane, right. If I look at it, if I look at the cross section, I am putting this atom, or this lattice position, it is not an atom really, this lattice site at about 1/3, 2/3 and 2/3. Okay. The other lattice site, which is the darker lattice site, I put at 2/3, 1/3 and 1/3. So this is at this is closer to the basal plane, because it is at 1/3, not at 2/3, right. And so along the A axis, I have a 2/3 of A hexagon and 1/3 of B hexagon, right. So I make 3 such entities, these 3 are in the same plane, right. So I can do the same thing in all the 4 unit cells. Then it turns out that these 3 AR, BR and CR are in the same plane, and so the white circles are in the same plane. So the black circles are in one plane, the white circles, and that plane is given as z equal to 1/3. The white circles are in another plane, which has z equal to 2/3, right. So now these are all my lattice points, right. So in a system with threefold symmetry, these are all the lattice points that I will have, right. So in some way, what I have done is I have taken a hexagonal unit cell, and I am trying to put points inside this hexagonal unit cell. So I have more than inside a hexagonal primitive, inside a hexagonal cell, I am putting more lattice points. So I am making I am going towards a non-primitive hexagonal unit cell. Okay. So because there are more than one, there is more than one lattice point in a hexagonal unit cell. Okay. So this is the concept of centering, which I am going to talk about in just after this, right. So or Bravais lattices, but in a hexagon, so you can center the hexagon, right. So in this following way that I just described, and then you can define another unit cell, right. So another unit cell, but this time this unit cell is actually a primitive unit cell. Now, this unit cell also captures the threefold axis of symmetry. So, I have A is this point here, right, whereas so I look at all my all the lattice points at 1/3, right. So, this is the 1/3 plane, the B, F and D, right. So, these are all the lattice points at Z equal to 1/3, and then sorry, B, D and F, right. So, B, D and F, correct. Whereas, so if I change the color now, let me ink color, let me change it to black, right. So, I have G, C and E, right. So, that is another plane which is okay. So, black, probably not black. Green maybe, right. So, G, E and C, right. So, that is, these are other set of lattice points, right, which is at Z equal to 2/3, right. So, I have 3 lattice points here, 3 lattice points here, and then I end up again, this is a unit cell translation, this is Z equal to 1, right. So, this is Z equal to 0, that is Z equal to 1. Okay. Now, I join all these corners in this way, right. So, I join A to B, A to F, A to D, right. Then I join A to this top A to G, top A to E, top A to C in that fashion, and then I start connecting these corners G to B, G to F, right. So, E to F, E to C and so on and so forth. So, I get a polyhedron, right. This polyhedron is nothing but it is a rhombohedron, right. It is a rhombohedron where the threefold axis is this axis. This is my, okay. So, let me again change the eraser, let me erase this portion and let me change the color. In color, let me make it this. So, it is a rhombohedron where I join A and A, and that is going to be my threefold axis. There is no sixfold axis here, because of this lattice centering I lose the sixfold axis of symmetry, right. There is a threefold axis of symmetry, however, and threefold axis I can define another unit cell, and this which retains this threefold axis of symmetry. That unit cell is primitive unit cell, and that is what is called a rhombohedral unit cell, and this is how you define the rhombohedral unit cell. Okay. Right. So, in general, so you can look at, let me right. So, I have a rhombohedral unit cell which instead of me drawing, right. So, this captures the threefold axis of symmetry. So, it is a perfectly good way of representing my system if it has a threefold axis of symmetry. Or very simply I can represent the rhombohedral system as a hexagonal system, as having a hexagonal unit cell with additional lattice points. Right. So, for example, I take this system, and I put my lattice points at 1/3 and 2/3 in these planes, right. So, Z equal to 2/3 and Z equal to 1/3. I put additional lattice points, and these lattice points are going to be at 2/3, 1/3, 1/3 and 1/3, 2/3, 2/3, right. So, at these positions if I put additional points, I can as well look at a rhombohedral unit cell as some sort of a centered hexagonal unit cell. Okay. So, these are equal, I mean, so you can represent it as a hexagonal unit cell which has centered lattice points, or as a rhombohedral unit cell. So both as the rhombohedron that we just defined from the so from the images that I showed you. Okay. So these are equivalent. Okay. So both of them will capture the threefold axis of symmetry. Okay. But again, so if you represent it in a hexagonal unit cell, the idea is not that you have a six-fold axis of symmetry, it is still that you have a threefold axis of symmetry, right. So if you center the hexagonal unit cell, you lose the six-fold axis of symmetry, you come to a threefold axis of symmetry. Okay. So now what is all this business of centering unit cells, right. So anyway, so just to finish off what we started before I go into centering properly. So we looked at 7 crystal systems, right. So from triclinic, which from now on I am going to call it A, monoclinic, which will be represented as M, then I have orthorhombic, which is O, then tetragonal system, which is T, then cubic, which is C, then I have trigonal or rhombohedral, I am just going to write it as rhombohedral, which is R, and hexagonal, which is H. I am going to call this systems as trigonal systems. Okay. So these are the 7 crystal systems, right, and so far we have been more or less saying that, okay, so we have not really considered, we said all these can be derived from symmetry. And from underlying symmetry, we have some constraints on the unit cells. Okay. And these constraints we said are, although I did not say it specifically until I spoke about the trigonal or rhombohedral systems, the systems with threefold and sixfold axis of symmetry. Mostly what I was talking about is primitive unit cells, constraints on primitive unit cells. Or unit cells that have or preferred unit cells, let us say, that have one lattice point. Okay. Now, I give you a lattice which is so a 2-dimensional lattice, which is somewhat like this. Let me try to draw it properly so that there is no confusion. Okay. Lattice points. So I am going to put lattice points, let us say more close to that, right. Sorry. Sorry. Okay. Whereas, so the motif, well, okay, so let us not worry too much about the motif right now, but you know, if this is my lattice, you know, there is if I want to define a unit cell, I can define a unit cell which is sort of you know, I can define a primitive unit cell, I said, right. So, a primitive unit cell can be defined like this, let us say, okay. Or I can also define a unit cell which is nice and rectangular, right. So, this is the non-primitive unit cell. And this non-primitive unit cell, you know, so I have axes that are at 90 degrees with respect to each other. So, if I, you know, if this, you know, so if I define it with again, so the if the system has an underlying symmetry which is a mirror or two mirrors or two-fold axis of symmetry, it makes sense, although I can define a primitive unit cell like this. This does not capture an underlying symmetry, underlying, let us say there is a two-fold axis of symmetries. Or two mirrors, okay. So, I can see some mirrors here. So, underlying two mirrors. Okay. Whereas, you know, so if there are underlying two mirrors, you know, so I said that the preferred, you know, if I have two underlying mirrors, you know, the unit cell constraints should be orthorhombic in nature, or alpha in 2 dimensions, alpha equal to 90 degrees, beta equal to 90 degrees, right. So, this will be a preferred unit cell, this will be a preferred unit cell. However, if I see in the primitive unit cell, alpha is not equal to you know, beta, you know, so in the primitive unit cell defined earlier, alpha is not equal to 90 degrees, beta is also not equal to 90 degrees, right. So, if there is an underlying symmetry which is two mirrors, right. So, then alpha and beta, you know, so this definition, I mean, so choosing this primitive unit cell is not good, okay. So, rather we have to go towards choosing non-primitive unit cells that actually show the symmetry of the system, okay. So, in other words, if you tell me that I have a unit cell with alpha equal to 90, beta equal to 90 in 2 dimensions, I am going to you know, already imagine that the underlying symmetry should have at least two mirrors or two-fold axis of symmetry or something like that, right. So, it is equivalent to an orthorhombic system in 3D. So, in 3D, if you tell me that I have a unit cell with alpha equal to beta equal to 90 degrees, I know, okay, so then I know that it is orthorhombic, and you know, I already have the idea that, you know, orthorhombic means the symmetry elements should be, you know, three two-fold axis of symmetry or three mirrors or whatever it is, right. So, or two mirrors and one two-fold axis of symmetry. So, I am already imagining the symmetry elements by just looking at the unit cell, right. So, even though unit cell does not tell me, you know, so periodically what is the motif, etc., all these things are not there, but still if you are telling me that there is an orthorhombic unit cell there, I am already imagining that the system has a symmetry which is 2 2 2, which has three two-fold axis of symmetry or two mirrors and a two-fold axis of symmetry, okay. So, so in that sense, you know, so it makes, you know, perfect sense if I have symmetry, which is in this case right. So, if it is two-fold axis of symmetry, it makes perfect sense to not consider the primitive unit cells and go to non-primitive unit cells like the let me draw it with a different color, the green unit cell here, right. The green unit cell is a rectangle, which means I have two angles which are well alpha, okay, so in this case it is one angle, but okay, so in 2 dimensions it's a rectangle, right. So, this rectangle is actually telling me that there is a mirror or there is a two-fold axis of symmetry, okay, in 2 dimensions. So, so this gives me the constraint. So, whereas this is not a rectangle. So, here my alpha is not equal to 90 degrees. So, let me not write alpha and beta because I am just doing it in 2 dimensions. Let me correct myself there. Let me just write alpha, okay. So, here also I am just going to say that alpha is not equal to 90 degrees, okay. So, it makes sense to capture the underlying symmetry that I define my lattice to be this lattice, my unit cell to be this unit cell and not the primitive unit cell, not any other primitive unit cell, okay. So, this gives me the concept of what is called centered lattices or centered unit cells. So, in this case there are 4 lattice points here, right, but I have another lattice point which is at the center of these 4 lattice points, right. So, this is a centered lattice and the unit cell does not unit cell has more than one lattice point. Or in other words, this is a non-primitive unit cell. Okay. But I am doing all this exercise sheerly because if there is an underlying symmetry, I should be either able to represent it as a primitive unit cell, right, which is one of these 7 unit cells that I have defined earlier, or if it is not possible to define a primitive unit cell, it is okay, but I am going to increase the number of lattice points in my unit cell and I am going to define a centered unit cell, right. And the centered unit cell should capture the two-fold axis of symmetry. So, if I have one two-fold axis of symmetry, my centered lattice should have the unit cell parameter such that alpha equal to beta equal to 90 degrees and gamma is not equal to 90 degrees. It is a monoclinic system, right. So, the unit cell should, just looking at the unit cell, I should get an idea of what the symmetry elements are, right. So, to capture the symmetry, so I would like to not go to a primitive unit cell all the time, but I can center the unit cells and go to a centered unit cell, right. So, that the axes are the way they should be, right. So, as we defined earlier. Okay. So, that is the motivation of defining what are called centered lattices or so these are also called Bravais lattices. Okay. Again, so Bravais lattices, we have 7 crystal systems and we have 14 Bravais lattices, which means so each of these crystal systems I am going to now split it as so the crystal system which can be centered or which cannot be centered, right. So, I will do that exercise in the next class, but we have 14 Bravais lattices, right. So, this is just to so a crystal system can either have a primitive unit cell or it can have a unit cell of choice which is non-primitive, right. And what are the different sorts of non-primitive unit cells that the crystal system can have, okay. So, there can be 14 different Bravais lattices, and so in the next class what we will look at is we will see how to form the Bravais lattices, what are the different kinds of centerings that one can do to a lattice. Okay. So, we will ask this question first, and how many of these centerings are compatible with my crystal system. With each of my 7 crystal systems. Okay. So, we will start with these 2 questions. It is okay if you do not understand what I am writing here right now, because in the next class anyway we are going to start by 7 crystal systems, and we are going to center each of these crystal systems differently, and we are going to prove to you that so the only number of Bravais lattices that can exist, which are all the lattices combined together, all the so the primitive lattices, the centered lattices in every crystal system, all of this will combine together give you 14 Bravais lattices, not more. Okay. So, so we'll start this exercise in the next class. Thank you.